In this video we're going to look at the solution to exact differential equations. Okay, and I recall this is a solution method to solve a differential equation that is of the following form. dy dt is equal to negative some function t, capital T, that depends on the variables t and y, divided by some function f that also depends on t and y. And so, for example, you can, as an example, consider the equation 1 minus 3 over y plus x dy dx, okay, plus y equals 3 over x minus 1. Now in this case we can see that instead of having dy dt we have dy dx, so x is our playing the role of t in this problem, and it is the dependent variable, and y is the, that's the independent variable and y is the dependent variable. Okay, so the way one would tackle this problem is to get this into differential equation into differential form, which involves multiplying both sides by, oh, this is capital Y, sorry, multiplying both sides by capital Y, okay, multiplying both sides by dt, and then adding the t to the other side equal to 0. So this is, and from here we would then be able to compute our vector field for this differential equation. Your vector field has a first entry, it's a function of t and y, and it has a second entry that depends on t and y. And in this case, it is, the first entry is the function t, and the second entry is the function y. Okay. So in this problem, okay, if we continue working down through this example, we'd have to get this differential equation into this form to then find our vector field. So I will continue down that process. We'll do 1 minus 3 over y plus x dy dx. Subtract y from both sides. Then multiply by dx. Okay. And then shift the dx to the other side with a minus sign, so you'll get negative 3 over x plus y plus 1 dx equal to 0. And therefore our vector field in this case depends on the variables x and y. The x entry comes first, so here is our function capital X, and it depends on x and y, and here is our function capital Y. It depends on x and y. Capital Y is the coefficient of the dy, capital X is the coefficient of dx. So this would be x comma y, and therefore our vector field is negative 3 over x plus y plus 1, 1 minus 3 over y plus x. Okay, so that's the end of step 1. Step 1 is to, step 1 will help you to find the vector field. Okay, that is your goal at the end of the first step. Once you have that first step, you have your vector field. Okay, you can continue through the notes, right, that we have put on our course page and that I've covered in class. You can work your way through. Now you know this vector field, you can go through the rest of this solution here. Here are the integrals that you need to do. So I will follow through these steps next. Okay, you can see there that there is we need to find our potential function by doing these integrals, and line equation number 6 here And then once you find your potential function, you will then just look at the level curves of it, and those will be your solution. So this is the steps we're going to go through now. Okay. So recall that what we had was that in general, right, once you have your vector field, right, the solution was to find your potential function, okay, and by doing the integral of t dt plus the integral of percent sign dy, where percent sign is equal to big function y minus the integral t, partial derivative of t with respect to y, and then integrate with respect to t. Okay, so that is the series of steps you would go through. Let's work through that for our specific example here. Okay, we would need to do phi, whoops, wrong pen, sorry about that. We would need to find phi as a function of x and y, and instead we would need to integrate the x entry with respect to x plus the integral of percent sign with respect to y, where percent sign is equal to function y minus the integral of the capital X function with respect to y dx. So these are the steps we need to go through to solve this problem. Okay, so I'm going to integrate x with respect to x. Integrating x with respect to x is the integral of -3 over x plus y plus 1 with respect to x. Do the integration here, and that will lead you to -3 logarithm of x plus xy plus x. There's your integral of x right here with respect to x. Okay. Now we need to compute, we need to find percent symbol. Percent is y. Y is 1 minus 3 over y plus x. Okay, this is y. Minus the integral of x partial derivative with respect to y dx. So here is our x, and we need to take the partial derivative of this with respect to x, okay, which is 3 over x squared. Okay. The partial derivative of -3 over x with respect to x, that comes from -3x to the -1, and then take the derivative will be 3 over x to the -2, which is 3 over x squared. Okay. So we can see that percent symbol is going to be 1 minus 3 over y plus x. And now we need to integrate 3 over x squared. And that should just become, integrate that with respect to x. Oh, sorry, back up. What goes here is the partial derivative of x with respect to y. So the partial derivative of x with respect to y is just 1 here. Sorry about that. Okay. Partial derivative of x with respect to y is 1, and therefore that becomes quite a bit easier for us actually to integrate 1 with respect to x, and you get x. And as promised, according to the notes, that the x's will cancel out and leave only a function of y. Okay. So we have found percent symbol, so to complete our potential function, we needed to here was the first part of our potential function, this. I need to add it to the, right here, the integral of percent symbol, which is 1 minus 3 over y dy. Integrate with respect to y, that would be y minus 3 logarithm of y. Okay. And now we have our potential function. It's a function of x and y. It is going to be the first block here and then the second block added to each other. And therefore you will get negative 3 logarithm of x plus xy plus x, and then add that to y minus 3 logarithm of y. There is your potential function. Okay. And solutions therefore, so the solutions therefore to the differential equation we were looking at, take that formula star. Okay. So phi of x comma y, let me look back at that, it was, so I can have it on this page, minus 3 log of x plus xy, minus 3 log of x, minus 3 logarithm of x plus xy, plus x, plus x, oh, what was the other? Plus y minus 3 log y. Plus y plus 3 logarithm of y. So then your solutions to the differential equation that we had written down were phi of x comma y equal to a constant. Okay, for any constant c. So 3 logarithm of x plus xy plus x plus y plus 3 logarithm of y equal to a constant. And so this would be your general solution. General solution. And if you would like to, perhaps if there was an initial condition given, you know, perhaps the initial condition had been given to y of 0 is equal to, you gotta be careful here, y of 1 is equal to, say, maybe 2. Okay. That would have helped you find the constant c. Would have helped you find that because this would have been x was equal to 1, y is equal to 2, so minus 3 logarithm of 1 plus 1 times 2 plus 1 plus 2 plus 3 logarithm of 2. That would be your constant. Logarithm of 1 is 0. 2 plus 3 plus, that'd be 5 plus 3 logarithm of 2 is equal to your constant. So this would be your specific number that would give you a specific solution to this initial condition problem. Okay, let me show you quickly how to check your answer to this differential equation. We have it on the screen there, but you could go to the demos on the website. And this is an exact equation. Okay, there was a potential function for it, right? How did we know there was a potential function? We knew that there was a potential function for it. Let me put this in another color here. We knew there was a potential function because this vector field, well, we found the potential function, but we could have also checked that right here, here's f1, the partial derivative of f1 with respect to x, does that in fact equal to f2 with respect to y? Partial of f1 with respect to x, oh sorry, f1y is equal to f2x, sorry about that. f1 with respect to y is equal to 1, f2 with respect to x is equal to 1, and since they are equal, you knew that there was a potential function. Okay. So that tells you that we have an exact equation, and we can then sorry, these were the steps I was just showing you. That the partial of f1 with respect to y is 1, and the partial of f2 with respect to x is also 1. Okay? So now we know that this is an exact equation. Okay? We went through the solution method using those techniques. You can put in your function f1. f1 is -3 divided by x, okay, plus y plus 1. This is from the algebra that we did on in the previous part of the notes. And then f2 is equal to 1 minus 3 divided by y plus x. Okay. And in this problem we also gave an initial condition. We said that x was 1 and y was 2. Okay. So you just change the differential equation by changing the vector field and then change the initial condition. You would highlight the cell, hit Shift Enter. Okay. All right, and here is the solution that I think that we wrote down on the previous page. You can see that f1y is equal to f2x. We went through this formula, computing all those integrals. Here was your potential function. Okay. And yes, I think that's what we had written down. Maybe off by a minus sign, but I think we are, let me see. Yes, I think we are correct. So here is your solution that you could check, and here would be the constant of integration. So you could look back through this problem and see if everything matches what you had done here. Okay, so that'd be the end of this exact differential equations video, and there's some issues here because of the plotting near 0. We have to be careful with logarithm of 0, but here you can see our solution following the contours here, and here are a bunch of other solutions through different initial conditions. Okay, so you have the ability now to do all the integrals and to check your answer using the differential equations, exact equations demo. Okay, so I will leave you to work through the rest of the homework problems that are in the notes. There are many here in the part of the notes on solving first order differential equations. Okay, so that would be the end of this video, and we will continue the next video by solving linear differential equation using exact techniques.